right, hello everyone. It's great to see so many faces here today. It's for this very exciting talk. So as a quick introduction, this is Dr. Spencer Frei. He's an assistant professor of statistics at UC Davis in the US. His research is on the foundations of deep learning, including topics related to benign overfitting, implicit regularization, and in-context learning. He was also named one of the rising stars of machine learning by the University of Maryland in 2022. So let's give him a big round of applause. Thank you for coming.
Thank you for the kind introduction and yeah, for inviting me to speak today. I'm going to be talking about some recent work with Ruiqi Zhang and Peter Bartlett, who are at UC Berkeley and DeepMind and UC Berkeley respectively. And the talk is going to be about learning linear models with transformers. Okay, so just going to make sure that we're all on the same page about these models. Transformers are the kind of backbone behind the things that everyone is talking about, these GPT chatbot type things. And they're a special neural network architecture that are distinguished from previous neural network architectures in that they can operate on sequences and output sequences. Right? So the kind of standard fully connected network or convolutional neural network that were really popular for the last 8 years or so were primarily things that mapped fixed vectors to fixed vectors, but now we can allow for sequences of vectors and mapping it to sequences of vectors using compositions of linear and nonlinear transformations. And the kind of way that these things are trained is by using internet data or any type of sequences of strings or anything that you can encode into vectors. And you try to have some type of fill-in-the-blank objective function, right? So you take internet data and you either randomly mask some words and you try to fill in the blank, or you give it a sentence and then you try and you chop off the last word and try to predict what the next word is. And so when you train on these with complex data and a few more bells and whistles, then you get these really kind of striking chatbots that can do great things. So for instance, here is I wanted to create this slide basically where I said I want a subfigure that says the chicken crossed the blank, and on one side and on the other side I want it to say the blank crossed the road, I put this into GPT-4 and it creates this LaTeX code that actually correctly compiles to make this. Right? It has a kind of weird approach. Right? It uses fixed picture, which is not what I would have done to create this slide, but it works and it saved me some Googling, basically. So that's the kind of way that they're trained at a high level. I'm going to get into some more details about what's actually happening in a bit. So let's imagine that we've now trained these models, and then we can look at what's happening at test time when we feed it in new sequences of data. And this, something that was really striking to people working on these large language models about 2 years ago was this behavior that's been come to be called in-context learning, which is you have this model that's been trained, right? You train this model for months on these huge data sets, and now you have a fixed model. You start feeding sequences of data, and it can appear to do very crazy things without changing any of the parameters to the model, right? So you could feed in this data that says dog is to perro as cat is to gato, and then put in human is to blank. And these models will generally be able to understand some type of functional relationship that exists in these few examples and kind of learn how to make predictions based on the examples of data that you give it. Right? And so you can think about abstracting this to providing the model with sequences of input-output pairs for some function f. And the function f is not specified, but it kind of learns to mimic the predictions of this function f in many settings. And so this is what's been called in-context learning. So the context are the examples that you're giving at test time, and the predictions are what you get. Right? And the important thing is you're just having a fixed model, supply this sequence of f of x pairs, and then it makes these predictions. Right? You're not changing the model itself. It's just operating on sequences after having been trained. And so a way to think about this is that because these models operate on sequences and they can output sequences, is that they have the capacity to act as supervised learning algorithms at test time.
I'm not sure I understood the second. So you're providing a natural language description of this function,
No. I mean, yeah, so here, this is like in the GPT-4 setting. You literally just say, like, dog is to Pero as cat is to gato as human is to blank. Human is to. Yeah. And then the transformer would output umano, right, in the setting. And we're just trying to abstract away what this type of behavior can kind of be captured mathematically as presenting x f of x pairs. And the idea is that it seems to have the ability to act as a supervised learning algorithm at test time, even without modifying the model itself, right? So you built this machine that basically can act as a learning algorithm when you provide it inputs, like a sequence of inputs. Okay, and yeah, so there's a lot of complex moving parts going on here, right? There's the way that they're actually trained in practice and the way that they actually behave in practice is, quite complex, right? How do you start to formalize what's going on with the data sets that they're trained on? Like, what is the distribution of data if you kind of think about a statistical learning perspective? And there's also not just the data itself, but the particular optimizers that we're using and the different types of architectures, right? There's a lot of different ways that, a lot of different knobs that you could tweak to make things behave in different ways. And so, where do we start to begin to try to understand what's going on is to first try to, abstract away and come up with some type of test case that we think captures important qualitative aspects of the models that we're looking at. Propose some simple models that fall within this framework, deeply understand those, and then after that, we kind of go back to the more complex settings and hopefully, we see whether our intuitions in the simple setting hold up, and if they don't, then maybe we need to revise our definitions and analyze some more complex models. Right? That's kind of the generic recipe of trying to understand these very complex systems that I've been trying to do and other people working in this area have been trying to do as well. So that's just kind of high level. I'm going to get more specific in the remainder. So we'll start with proposing some definitions of this idea of training on in-context examples, and then also testing or learning a function class in context. And then we'll look at this simple model of linear models so we'll look at what happens when you're training on kind of random instances of linear regression, and then you're testing on random instances of linear regression using a transformer that has only linear components to it. Okay, so there's a lot of simplifications that go on there, but we can actually say a lot in this setting. And we'll be able to not just say what's happening during training for this like non-convex optimization problem, but we'll be able to very precisely characterize what's going on at test time. And then we'll kind of look into what's happening, what are the differences between this simplified linear model and what happens if you use like a GPT-2 or GPT-3 style architecture for similar tasks, and whether or not our intuitions from the simpler setting hold. Okay, so is that good for outline? And then next I'm going to get more specific. Okay, so yeah, as I said, there's kind of a disconnect between the way that transformers are actually trained in practice and this observed in-context learning behavior, right? I mean, maybe it's the case that on the internet that all these transformers were trained on, there were literally like tables of input-output function pairs that have very similar behavior to what people have observed in practice, right? That's maybe true, but it's also it might not be the case. And I think, so if we really want to understand what's going on, let's first simplify things and look at what's happening if we really have something similar to what's happening at training time and what's happening at test time. Okay, so to make this more specific, we'll look at what's happening if we train on what we call random instances of supervised learning tasks, and then we test on another random instance of a supervised learning task. Okay, and I'll formalize what I mean by random instance of a supervised learning task in a second. Right, but this is really what was, there's this remarkable paper by Shivam Garg, Dimitris Tsipras, Greg Valiant, and Percy Lang from last year that was a purely experimental paper, but really is what got me thinking about this problem and a lot of other people interested in trying to develop some statistical theory for these types of in-context learning problems. So the framework is as follows. We have some function class, h, and we have some fixed distribution over features, dx. And then we imagine that we have a distribution over functions in this function class. Okay? And what we imagine is that the learner gets access to random instances of supervised learning tasks determined by random functions drawn from this distribution over hypotheses. Right? So imagine you have some type of distribution over functions, you sample a function, and then you sample features, and then you're given different instances of what would be like a standard kind of supervised learning task where you have training data and the form x, h of x, and then you have a prediction that query example that you want to make predictions on. Right? And let's imagine we have b IID instances of these supervised learning data sets of size n. Okay? And we're going to train a transformer on this data. And the question is, if we then have trained on this data and we take some new supervised learning task by sampling a new random function h, new random features, or new features xi's from the same distributions, is it the case that this trained model will be able to make predictions correctly? Right? Will it have small loss based on whatever loss function you care about? Okay, so is this setup at a high level, does this kind of make sense?
Can I think about it maybe, if you parameterize these functions, right? Can I think about it as a gigantic input space, right? Parameters of the function, inputs, and a sample in there.
Yeah, sure.
And then I have some master function that maps everything.
Yeah, so I mean, it's not clear that that's how the transformers will work, but that's a way of interpreting it, yeah?
I mean, wouldn't you think of kind of like bringing in the gradient descent in the loop? Like you take those data sets, you run a gradient descent to approximate the approximate class, and then in context learning would be somehow would the in context learner then basically implicitly run, like you'd imagine that it would implicitly be running a gradient descent to making the next prediction.
Yeah. So that's like an interpretation that people have. We'll get to a bit more formal on that in a second. But you do gradient descent. Like you take this data, you form an empirical risk defined over a transformer architecture, and you do gradient descent over this data.
Oh, okay.
You literally do gradient descent over this data, but at test time, you're going to be given a new model, and then it kind of, but at test time, it basically can behave like a learning algorithm. So there have been like a line of work that say like after you train, these networks actually behave like gradient descent. What they'll do is they'll take this data set, like you'll take like a fixed data set and then do gradient descent over it. But this is a bit complex, and I think it'll be easier once we actually talk about what model we're using. Okay. Great, and so I just want to maybe hammer home the point of what is the difference between this in-context learning with more classical supervised learning frameworks, right? And so at a high level, when I've described what in-context learning of a function class is, it's not any different than the classical paradigm of supervised learning, right? Like what is in-context learning is it takes a data set of examples, of input-output examples, and it forms predictions for test examples, right? In that sense, ordinary least squares in context learns like linear functions, right? Ordinary least squares takes in x, y pairs, does this x transpose x inverse, x transpose y, and it uses that to form predictions for examples, right? That's really not all that different than what we're used to. The real novelty is the fact that you can train on random instances of these kind of learning tasks and then get a model which can operate as a learning algorithm at test time. Right? Like it's the fact that you can train on random data sets and then have this kind of test time behavior that otherwise you need to encode prior knowledge of in the classical supervised learning paradigm. Okay, so now I'm going to get into the specific neural net architectures that we look at and what we showed. Okay, so we'll look at features that are in RD. And we have some space of functions from RD to R, and we have a loss function. We have a distribution over the features, distribution over the hypothesis class. And then we have some type of function that can operate on sequences. Right? So think of this as the transformer with attention. We train on B supervised learning tasks. Right? So we sample the function from the function class, sample the features, get B data sets of size n. Right, so we have n samples within each data set, and we have b different kind of random tasks. And then we train by trying to minimize the loss that we can form using this like prompt of examples, right? So we'll call this the sequence of XY pairs as a prompt. Right? And so this is a stochastic optimization problem. Right? So any stochastic optimization problem, you could try to solve it using stochastic gradient descent by just doing gradient updates over each data set. And hopefully you can find a minimum. Maybe you can't find a minimum. Maybe you find a stationary point. But let's just consider what happens if you do find a minimum. And then we want to look at the test time behavior by taking, sampling a new random function, new features, and then looking at the expected loss under that distribution and for that loss function.
Sorry, at test time, are you changing the distribution of the functions of the features, or are you sampling new ones?
Sampling new ones from the same thing.
So
Yep.
you're looking at the generalization.
Yeah. But what we'll also look at is what happens if you have like out of distribution shift. Like what happens? Yeah, we'll talk about that. But for now, let's just consider just the same setting in training and test time. Okay, so yeah. Yeah, different functions, but from the same function class. Like so, for instance, we can consider this H as linear models, right? Let's say H is going to be something that maps features X to W transpose X. And then we have a distribution over vectors in RD. Right? Let's say we take isotropic Gaussian weights. And then so we sample an isotropic weight vector from a Gaussian. And then we form these data sets of Xi, W transpose Xi. Right? So that W is going to be fixed across this whole, this one data set. But for different tasks, you're going to have different random weights that determine the kind of the function. I mean, it's kind of up to whatever the distribution you choose is, right? But if you think about the weights being IID Gaussians, right? I mean, they're just IID Gaussians, right? They are as similar as IID Gaussians are, which like they're kind of orthogonal, but not really, not precisely. Okay, so the question here is, the kind of statistical question here is how many examples do we need from all these different perspectives, right? How many random tasks do we need? How large do the training context at training when we're training on these things? How many examples do we need for each task? And then at test time, how many examples do we need in order to achieve small prediction error? Mm-hmm.
We're probably going to hand out mics just so that people online can also hear, so we'll try to do that for now.
Okay. So by giving n samples, do you mean like the n samples are given as a context when doing each prediction?
Yeah. So at training time, you're given b different data sets of size n.
So is it possible that like even those n samples can be from different functions instead of one function?
Yeah. So within each task, it's the same function, right? So we first sample a function, and then we create one data set by taking x, y pairs where y is equal to that function of x, right? So y is equal to h of x. Within each data set, the h is fixed. But across data sets, the function that is determining the labels differs, right? Because you're sampling it from a distribution.
Is it possible that like you can have even when giving in test time, when given a various samples for in-context learning, it's also possible that the function is not deterministic. Like for one sample, you can have such a function, and for another sample, you can have another function.
So you can we'll talk about that a bit about how do you examine at test time if it differs from what's happening during training. But we can quantify what's happening in that setting. Yeah.
Okay, thank you.
Yep.
I wanted to understand the notation there. So f theta of p.
Sorry, f theta. Yeah.
So h of x query, understand, it's the label or whatever for that x query under the function h. But f theta is something that takes in this string and produces a prediction for x query. So it's itself a learning algorithm, right?
Yeah.
Okay, and so the theta is really the parameters of the learning algorithm, not of the...
No.
Okay.
Theta is the parameters of the neural network.
Right, but I see. So you're not training it there. You're just saying...
So you train over the parameters of the neural network architecture, but the striking thing is that the neural network is able to act as a learning algorithm without changing its weights.
I got it. I understand. So basically, the neural network takes in this whole string. I was thinking more about taking in each x, hx. Okay.
Yeah, no, it takes in a sequence.
A sequence. It's really like a sequence. Okay.
Yeah. So I'm going to maybe just go to the next few slides, and maybe I think some of these questions will be better understood. So first, I'm going to talk about what these Garg and what the Garg-Cypress papers found, which is, as you can imagine, you have different function classes, right? You can imagine taking linear functions. You could take tree-structured functions. You could take functions that are two-layer neural networks, right? That map an input to a two-layer to the output of a two-layer neural network. And what they show in this graph is what happens if you take linear models as the function class. Okay, and this is training a GPT-2 transformer on random instances of linear regression, right? So where the weight vectors for a fixed task are sampled from an isotropic Gaussian. Okay, and what they show here is they're comparing what's happening with the transformer. So this is 20-dimensional linear regression, noiseless linear regression. Right, so noiseless linear regression, in order to perform optimally, you just need d examples, right? The number of samples needs to be the dimension. And what they show is that, and least squares achieves that, right? If you do ordinary least squares in noiseless linear regression, n equals d samples is enough to perform optimally. And so in blue is the transformer, and in orange is ordinary least squares. And what you see is that the transformer behaves almost exactly like ordinary least squares. Right, so this is at test time, after we trained on random instances of linear regression. Now we have this transformer which can take as its input sequences of data, and we're giving it data sets that are another random instance of linear regression and seeing what its performance is. And what you see is that it performs almost exactly the same as ordinary least squares. Okay, so and this was, I think, the thing that really kind of put fire in a lot of people's eyes, is like, it's kind of crazy that this transformer behaves like this very familiar learning algorithm that is ordinary least squares, right? I mean, its test curve is almost exactly the same. Right? And this is a very complex, 12-layer transformer with 20 attention heads or something, and it does very well. And you can think of, and in this paper, they also looked at various other versions of this, like what happens with two-layer neural nets. They looked at sparse linear regression and actually found that it performs similar to an optimally tuned lasso. Right? So it actually adapts to the sparsity in the problem. It does better than, they looked at tree-structured data and found that it does better than all known standard tree learning algorithms like CART or random forests. It's really, so this paper was really fantastic and really was the inspiration for us to try to understand better what's going on here. Okay, and so now I'm going to get into math and say what we actually did, and maybe this will clear up some of the questions that people were having. Okay, so for each task tau, we're going to index different tasks. A task will correspond to a single supervised learning data set. Right, so we have a prompt that consists of xy pairs, n xy pairs, and then a query example that we want to make predictions for. Okay, so the transformer operates on sequences, and we have the option of choosing how to form what sequence to give to the transformer. And so what we'll do is we'll concatenate the xy pairs into a single vector and feed the first n examples as columns. And then for the final column, we're going to have the query and then a 0. Okay? And the goal, right, transformers can map sequences to sequences. And so what we're going to use as the prediction for x query is the bottom right output of the transformer. Okay, so what is the building block of these transformer architectures are these attention blocks that have these parameters wk, wq, wp, wv, and then a softmax, right? So this is the kind of standard one-head attention layer that people have. And we're going to be making a number of simplifications to this model. First is that we're getting rid of the softmax. We're merging the two matrices into one, and we're merging those two matrices into one. Okay? And so you can see that this model takes sequences and outputs sequences. And we're going to use this to try to formulate a kind of squared loss objective that says that, that'll get you in the next slide of exactly like what the objective function we have is. So is this kind of clear so far? OK. Great. And so the training setup is that we have noiseless linear regression data. So for each task, we sample a weight vector W from an isotropic Gaussian. And we sample possibly anisotropic features. And then the labels are given by W tau transpose X, right, for each task. Okay. And we're going to look at what happens in the infinite task limit. Right? So as the number of tasks that you have goes to infinity, we're going to look at gradient flow over the resulting objective function. Right? So we are going to take the prediction for some task, subtract out the ground truth label, and then use the squared loss. Right? So there should be a big block around that. Sorry. Right? And we'll look at what happens when you do gradient flow over this population objective. So does that make sense, right? We would form an empirical risk, take the number of tasks to infinity limit, and then see what happens with gradient flow. OK, so there's some technical conditions that we need for how we initialize gradient flow. It's not all that important. The important thing is that we can allow for some randomness in the initialization, and that this is not encoding the solution into the initialization. It really learns something quite different. It's kind of technical. I'm not going to get into that unless people have questions towards the end.
Maybe you could just say whether this objective is convex.
Oh.
Is this objective convex?
No, this objective is not convex. Yeah, so that's a good question. Yeah, so it is not convex, even though because we have these products of matrices. When you have products of matrices, it's non-convex. Yeah. OK. All right, so here's our first main theorem, which is that if we have gradient flow defined previously with that initialization, and this initialization scale is small enough, then gradient flow converges to a global minimum of the objective function. And we can identify exactly what the weight vectors converge to. Okay, so there's a formula for what the weight vectors converge to. It's fine. It's not that helpful. But the thing that's more helpful is what happens if we have a new task at test time, right? Now, since we know what the weight vectors converge to, we can exactly calculate what are the predictions going to be for a new linear regression task. Right? So this is the in-distribution setting. We again have a noiseless linear regression task, same anisotropic Gaussian features, labels given by W transpose X. And what we show is that the predictions for this label, for the query example, are exactly given by this equation, which is this W transpose times kind of empirical covariance matrix times gamma inverse and then X query. Okay, so what is this gamma? This gamma is here in the blue, right? So gamma is a kind of regularized version of the covariance matrix lambda, right? Where as n goes to infinity, gamma converges to lambda. Right, n, if you remember, is how many examples we trained on for each task. And capital M here is how many examples we have at test time. Right, so they might be different. Maybe we train on contexts that are really long, and then we test on shorter contexts. Right, and so the kind of way that we can interpret this is that if the training prompt is large, so if n is large, then we have that gamma is close to lambda. So this gamma inverse is close to lambda inverse. If m is large, then this empirical covariance matrix is going to be close to the real covariance matrix. And so then we have lambda, lambda inverse, and then we get exactly W transpose X query, which is the correct thing to do. Okay. So this is what happens if we are kind of in distribution in the sense that our test time task looks exactly like the things that we trained on. But the nice thing is, since we can exactly calculate what these WPV star and WKQ star are, we can actually exactly characterize what is going to happen for any task that you're given at test time, without any assumptions on the data at all. Right, so first let's consider a slightly more general setting, where instead of assuming that we have a joint distribution over xy where y given x is linear, let's not assume that y given x is linear, but assume an arbitrary distribution over x and y. And then let's assume again that we have IID examples, but now possibly y given x is nonlinear. Right, and we have this same kind of, we're looking at what's happening with the trained transformer that we found by training on noiseless linear regression tasks. Now we're looking at what happens when we test on possibly not linear regression tasks. Right, what learning algorithm does it encode? Right, so basically what happens is that you have this X query transpose, gamma inverse, times the average of yi xi. Okay, and as m goes to infinity, since the data is IID, this converges to the expectation. Right, and actually what this yields is that your predictions are equal to the best linear predictor over your test prompt. Right, and I think this is quite cool. This is a kind of similar to what people call like emergent behavior in transformers, because we're just training on noiseless linear regression. But by training on noiseless linear regression, you get an algorithm which does basically optimally over, again, with respect to being a linear model at test time. Right? So imagine you have some like noisy data, noisy linear regression at test time. It's going to perform comparably to the optimal linear model, which is what's happening without noise. Which is kind of crazy because typically we think of very different very different learning algorithms that one would use if you have noiseless linear regression or noisy linear regression. Right? One setting OLS works, one setting optimally tuned ridge regression is the thing that works well. Right? So these are the kind of striking behavior of the trained transformer. Okay, so we had a bunch of approximate symbols across the previous slide. Yeah. Do you want to use the microphone?
I'm wondering if there is anything special about transformers in what you're talking about, or it can be somehow abstracted to generic architectures.
Yeah, that's a good question. I mean, so when we tried to formulate the questions here, we tried to make it so that we can consider this framework for any model, right? Like as long as it's a model that operates over sequences of data, it has the capacity to operate as a supervised learning algorithm, and you could form these same objective functions. No one has been able to find other architectures that work well for this, right? So RNNs have been around for a long time, but no one has gotten these to work as well with recurrent neural networks as they have with transformers. It's definitely possible that there are other architectures that could do this, but no one has figured out the kind of recipe to make them work. While we do have a recipe for these to work in this setting.
That's just a simple question. What would happen if you change the objective of the transformer to make the prediction to be the optimal linear weight? So namely, if you took the data set and then you ran the least squares, and the transformer just has to predict from the data set to the weight, surely that would be it would guarantee that it would learn. Well, you would think that it would learn the optimal least square because you're literally saying just reproduce that weight. This is doing something more. It's learning the algorithm in some sense, but that would be an easier task. Has anyone checked?
I'm not sure. I feel like this, I don't think people have tried that, but I think this is more flexible because it's not dependent upon like having an identifiable parametric problem, right? Like this, you could think of having some non-parametric function, and like in your function class, right? Like that takes x to h of x. You don't necessarily have to assume something parametric, and so generalizing from trying to predict the parameters to a setting where either the parameters are not identifiable or it's non-parametric is, yeah, I guess the kind of drawback of that approach.
I see. Okay, thank you.
Okay. Okay, I'm doing okay on time. So yeah, we had a bunch of approximation symbols across all the previous slides saying that as long as n is large enough and if m is large enough, then these things hold. We can make these approximations exact. Right? We can actually show that in this setting where you have an arbitrary distribution over xy with very minor conditions on the marginal, then the expected prediction error is going to be the best possible prediction error for a linear predictor, plus something that decays with m and something that decays with n squared. Right, so something that's kind of interesting here is that there are different rates for what's happening training time versus test time. This is kind of cheating a little bit because we have assumed infinite tasks, right? So we already assumed infinite training data, basically. So it's a bit of a cheat to say that it's 1 over n squared. But I do think it's still, there might be something there. Some work came out in the past few days that looks at what happens in the finite task setting, like to quantify the sample complexity of finite tasks. And I just wanted to maybe, to say like, we're in this in-distribution setting where linear model that's noiseless, this term in the red is 0. And the kind of sample complexities that you get depend upon the dimension and the trace and the ill-conditionedness of your matrix. So this is not the optimal regression. This is not the optimal sample complexity for linear regression. It's like a decent sample complexity for linear regression. But it does come close to the optimal error for a linear predictor. Right? So it's kind of a bit of a distinction. OK. And now I just want to talk a bit about some of distribution shift, which had come up in a few of these questions. Right? Since we can say, since we have the parameters, since we know what parameters it converges to, we can quantify what's happening on any prompt. Right? So now we're assuming that we have some sequence of, at test time, we have a sequence of pairs x, y, and then x query. And we don't assume anything about the x's or the y's. Okay? They could be arbitrary vector and scalars. Right? So the y's are scalars and the x's are vectors. And then what we have is that this prediction is given by exactly this, x query transpose, and then this gamma term that appeared before, which is like a regularized version of lambda, and the empirical average of yi xi. Right? So in the infinite context during training limit, this converges to lambda inverse. Right? We're not, like training, we know that everything is IID, so taking the n infinity limit is fine. Well, actually, there's not even any samples appearing here, right? There's just n. And what we have is this prediction that's lambda inverse empirical average of yi xi. Okay, and so a kind of nice thing is that, so in the Garg-Cyprus paper, they looked at the performance of these nonlinear deep transformers and looked at what happens under distribution shift. And basically, every single behavior that they found in these nonlinear transformers, like either the success under distribution shift or the failure under distribution shift, is satisfied by this model. And I think that it was a thing that we did not expect, but basically every type of thing that they looked at, you can basically see with this model here. Right? So for instance, the fact that it does well in noisy linear regression, which I mentioned before, then we can read it off from this equation. You can imagine if at test time you have some x feature that is x query feature that is orthogonal to the sequence of vectors xi, then the predictions are going to be 0, and that's exactly what happens here. And something else that they noticed, like basically the transformer does well under a lot of distribution shift, but one that did not do well on in the nonlinear architecture, and that we can see here, is covariate shift. Right? So that's what happens if the marginal features during training is different than the marginal features at test time. Right? And it's pretty easy to see off here, even if everything is IID in the same way as before, and it's still a linear model, if the covariance matrix at test time is different than training time, right, then you're going to have this lambda inverse lambda tilde, and things are not going to cancel out in the right way. Right? Basically, the transformer during training learned to scale the data in a certain way that works well for when things are in distribution, but the scaling will break if the covariance matrix at test time is different. Okay, so this was observed not just that's not just something that holds in the trained linear transformers, but was observed in these more complex transformers, and kind of natural objection to this being a surprising thing is that well, you're only training on things that had a covariance matrix of lambda, and so why would you expect to be able to perform well on different covariance matrices at test time? Right? So a kind of natural question is, well, what happens if you start to train on, say, different types of covariance matrices? Right? Maybe if you start training on different types of covariance matrices, there will be greater robustness to covariance shift at test time, and maybe it will learn a kind of more robust learning algorithm, right? That can actually do some type of, when you're given a sequence of data, it learns the correct covariance matrix, and then it implements an algorithm using that correct covariance matrix. So that's something that we looked at with these linear transformers, is what happens if you start to introduce a kind of distribution over covariance matrices. Right, so we have some type of distribution over, let's say, diagonal positive definite matrices with a few moments. And then we sample a covariance matrix, and then we sample a weight vector. And then we have features that come from this covariance matrix, Gaussian, and the labels that are Y transpose X. And what we looked at is, again, with gradient flow with the same kind of initialization as before, and looked at the task going to infinity limit. And when we do this, we can show that gradient flow does find a global minimum, and we can identify what its predictions look like because we can identify the parameters. But unfortunately, this is, at least for the linear transformer, this is not enough. So it's easy to construct examples where this trained transformer, even though it was seeing different covariance matrices during training, is not robust to covariance shift. Right? So a kind of simple example that, this is just a bunch of equations, but you can think about what's happening if you're training on exponential, where the covariance matrices are diagonal with the exponential 1 entries on the diagonal, and then you test on exponential 1 matrices on the diagonal, and it does not perform well. Right? It basically, the predictions are off by a scalar, a scalar multiple. Okay, so that's the linear transformer. Question is like, well, what happens if you start to train these real transformers on varying covariance matrices? So what we'll look at is a lot of information, but so we'll look at kind of two things, right? What's happening if you're training on isotropic Gaussians, and what's happening if you're training on Gaussians that have random covariance matrices, where the entries are exponential 1 on the diagonal. Okay. And then we're going to test on a variety of settings. We're going to test on when the covariance matrices are random with exponential 1, or multiples of exponential 1, where we're going to increase the multiple of exponential 1 to kind of increase the variance in the problem. Right, so the thing to note is that ordinary least squares in linear regression, in noiseless linear regression, does not depend upon the noise level, right? Like in terms of the variance. Like if you're increasing the variance of this sigma, right? If we're looking at a diagonal matrix with sigma times exponential of 1, as we increase sigma, ordinary least squares performs the same, right? N equals d examples is still optimal and necessary and sufficient in order to perform well. Okay? And what we'll look at is what happens if we're training on context lengths of size 70 and the dimension is 20. Okay, so there's a lot of information here, but first we'll look here. Okay, so this is random covariance. We're testing on random covariance, and the expected variance is 1, right? So sigma squared is equal to 1 here. Okay, let's pretend that we're not looking at anything beyond 70. So for the moment, just do not look past 70. What you see is that so in green is least squares, orange is testing on random covariance, blue is training on random covariance. Sorry, orange is training on random covariance, and blue is training on fixed covariance. And what you see is that when the expected variance is 1, least squares, training on random covariance, and training on fixed covariance all behave the same, up to 70. Okay, and again, just pretend after 70 doesn't exist for a minute. Okay, and as we go to the right, we increase the expected variance. Right, so we're going from sigma squared equals 1 to sigma squared equals 4. And what we see here is that training on fixed covariance does not do well. Right? It does not do as well as least squares. But training on random covariance does do well, although there's a little bit of a gap with ordinary least squares that exactly d equals at n equals 20. But it's still doing pretty well, again, forgetting what's happening after 70. And then when we increase the expected variance 9, we see that both training on fixed covariance does poorly and training on random covariance does poorly as well. Right, so what is the takeaway from those? Is that training on random covariance helps, but it's not enough. Right? You're not going to be able to actually match the performance of least squares. It's doing some other weird learning algorithm that's like a little bit robust to the different types of covariance matrices that you see, but is still not the kind of correct thing that you would expect. Okay, so then there's the caveat of what's happening after 70. Right? So we just trained on prompts of length 70. Right? So we're testing on prompts of bigger than 70. Right? And so what it's saying is that actually, like, when you test on prompts that are longer than what you're trained on, your performance can spike. Right? And the reason for this is because these GPT-2 models have these positional encoders in them. Right? So the standard transformer architecture, you take in your features, and then you also add these features that basically tell you what part of the sequence you're in. Are you at the beginning of the sequence or the end of the sequence? And these things are very poorly behaved when you go from fixed training context to a larger training context. So basically, if you get rid of these kind of positional encoders, then these gaps kind of disappear. Right? But the kind of out-of-the-box way that people train transformers results in this weird behavior once you start testing on prompts that are longer than you see during training. So a lot of things going on there, but I hope some of those takeaways are clear. Okay, I'm just going to very quickly say some words about how we actually prove things, but not go into a lot of depth, just so we have some time for questions. The kind of high-level idea is of how the proof works is that we first, what do we show? We show that global convergence of gradient flow, and then we have this characterization of the kind of statistical complexity for new tasks at the global minimum of gradient flow. And so there's kind of two parts to the proof. The first is to say, when you have a global minimum, it has a very nice, there's a very nice optimization landscape in the sense that global minima of the subjective function do something nice for new learning tasks, right? And so basically for any test prompt of the form x w transpose x xm w transpose xm x query makes this type of prediction, right? Which is x query transpose gamma inverse, which converges to lambda inverse as n goes to infinity, and then the empirical covariance matrix of your data times the weight factor w. Right, so this is the formula that we showed before. And that's the kind of first thing to do is say that at any global minimum, this is what happens. So that means that if you are able to actually solve optimization, then you do something reasonable for linear regression.
Thank you. The I in xi, when you take the sum from 1 to m, the I, is it the time step of the sequence, or is it the data, the index of the data sample?
So you get a data set. Your prompt is x1 w transpose x1 ... xm w transpose xm.
So x1 is a vector or is a sequence?
It's a vector.
Okay, so you're looking at sequences that of infinite length when you let m go to infinity?
As capital N goes to infinity, it's a sequence of infinite length. Yeah. So yeah, I mean, such a thing doesn't exist, but that we have in the previous slides we had some like guarantees for how the approximation looks for finite n and finite m. Right?
Thanks.
Okay, so that's the kind of first thing is we've reduced the problem to showing global convergence of a non-convex problem, which usually is not cause for celebration, but we are actually able to establish this global convergence with a Polyak-Loyasevich inequality. So what that means is that we can say that the gradient norm squared is bigger than or equal to some constant times the gap between the objective function value and the best possible value for that objective function. Right? Once you have a PL inequality, gradient flow finds stationary points, so it drives the gradient norm to 0. Driving the gradient norm to 0 means that you drive the gap between the objective function value and the best possible objective function value to 0, which means that you converge to something that has the global minimum value. Right? Once you have a global minimum, you get this nice learning algorithm at test time. Okay, so just going to conclude and hopefully give people some time to ask questions, and I can go further into the proof if people would like to. What we did is we tried to formalize what is this in-context learning phenomenon that has been observed in these real large language models, and try to distinguish between what's happening during training versus at test time. Right? We saw that even when you're training on a relatively simple task, you can get some kind of emergent behavior on your test time task. Right? Even though you're training on noiseless linear regression, you can do well on noisy linear regression or even nonlinear regression. Right? And what did we look at were these linear transformers trained by gradient flow on these in-context examples of linear models. And we showed that these can kind of learn to do linear regression in context. Right? And how did we do this is showing that despite non-convexity, gradient flow finds a global minimum. And then at this global minimum, it encodes a learning algorithm that does quite well. Right? And we saw that it's robust to some distribution shifts, but not all. And because of that, we were kind of motivated to look at what happens if you start to introduce additional randomness during training that has different types of covariate distributions, in the hopes that this would allow for some more robustness to covariate shift at test time. We saw for linear transformers it wasn't enough, but in the deep nonlinear transformers it does seem to help. Right? It's not the solution, but it does seem to help. And what I think are some interesting future directions are some obvious things that one might think of. We made a lot of simplifying assumptions when we were looking at these models. Right? We assumed infinite tasks. We looked at gradient flow, not gradient descent. We got rid of the softmax. We were just looking at a single layer, not deeper ones. All of these things I think are interesting. I should say that 2 days ago there was some work by Peter Bartlett, who's a co-author on this paper, with a few other authors, looked at what happens with finite tasks and with stochastic gradient descent, and quantified how many tasks you need during pre-training in order to do well at test time. So it's a very fast-moving area, but these are still open questions. There's a lot of different variants of these transformers that I think someone in the audience was asking about before, like what happens if you have a different objective function. You can think about trying to predict just the next prediction instead of giving a fixed sequence of length n, and you can imagine gradually increasing the length of your sequence and trying to predict just given, say, 5 examples, then 6 examples, and 7 examples. That is a different objective function and is more similar to this family of language models called causal language models. The dynamics of those are different. We should expect that they encode different learning algorithms, but people have not explored what actually happens in that setting. And yeah, I think this idea of how do we increase the robustness of these models and what is the real source of the brittleness of them is an exciting question. So we looked at what happens if you just change the, say, covariance matrix of these Gaussians. But another natural question is, what about different families of distributions, right? What if we want to generalize, well, not just on Gaussians, but like, say, log concave distributions or some other large family of distributions where maybe it would help to start training on different types of augmentations of your data or different types of families of distributions in order to increase robustness. Okay, and just last thing. I think, so there's been a series of works over the past few years about, since transformers can implement supervised learning algorithms, people have looked at kind of approximation theoretic guarantees of how do you implement certain supervised learning algorithms using transformers. Right? So you can think about how do you wire up a transformer to do lasso, or ordinary least squares, or a reinforcement learning problem. Right? So you can come up with a construction of how to do that. Right? But the construction of how to do it is not necessarily the same as how it actually does it if you train on random examples from in this kind of context learning setup. And so this is there's a lot of, in the deep learning theory literature, there's a lot of these kind of separations, like approximation, optimization separations. And those were mainly in the supervised learning setting, but now we have this kind of learning algorithm setting of how transformers can implement learning algorithms theoretically versus how they actually do when you train on tasks to kind of simulate this kind of learning of a learning algorithm procedure. And I think this is closely related to what is the kind of implicit regularization or implicit bias of gradient flow and gradient descent. Right? Given there are many different ways to implement, many different learning algorithms that could be implemented, which are the ones that these transformers actually implement when you train them? Right? That's the kind of the big question in transformers, and it's really, there's very, very little out there on that. And with that, yeah, I'm happy to conclude and take any questions that you all have.
If you have a question, just raise your hand and I'll bring the mic over.
Thank you for the great talk. I'm not from the computer science background. I'm doing materials, but sometimes we also use the large language model to extract the information from literatures.
From what, sorry?
To extract the information from literatures.
Literature.
Yeah. From my experience, we found that different large language model can have different performance. So why here you choose GPT-2, not like 3.5 or 4 or Llama or other?
Yeah. It's basically a resources question. These experiments could be done on a couple dozen hours of a consumer GPU, which translates into a few $100s of cloud computing credits. But if you wanted to do the same with GPT-4, because the other thing is we want to design these experiments from scratch. Right? We don't want to take a trained model that exists, like say GPT-4 from OpenAI or Claude or whatever, and look at what's happening with linear regression. We want to exactly say what's happening if you train on these functions in this either linear functions or whatever decision tree is 2-layer neural networks. And if you want to train a large language model on data, then they cost millions of dollars to train GPT-4 style things, and this is a measly academic budget version of that.
Your final objective, the final model, the Y query, looked, yes, to me quite similar to what you would get with a kernel machine. Is there, and we know, there is quite a large body of literature that studies infinite width limits of random neural nets, and in the end you get kernel machines, and so is there a link with that literature that you are making?
No. Yeah. No. So there's nothing related to neural tangent kernel here. The most immediate way to see that is that we allow for initializations with small variance. So all neural tangent kernel approximations break when you do that. But there is, something interesting is these models. Where is it? Great. So these models. So these embedding matrices have these features and labels in them, right? And you can think about E transpose E is kind of forming a gram matrix, except you're learning a linear mapping of the features into the same space. Okay, so in a sense, a 2-layer, a 1-layer linear transformer like this is learning to do the correct like kernelization using just linear transformations. And that's kind of what's going on, but that's kind of a after the fact analysis. Like you can say, like, I mean, I guess you can say that that's like why we might expect a single layer of a linear transformer to be able to do well for linear regression, because we know that if you have a kernel, like if you form a gram matrix correctly and you do things, then you can do linear regression. But there's not a direct connection to like neural tangent kernel here.
Thanks.
I could ask a question. So I saw that when you explained about the proof, that was more just getting global convergence of the objective. But then in order to do all of the once you know that it converges, if you didn't have the explicit form of the test prediction, do you think that there is any hope of being able to analyze the behavior? Because you might say, okay, let's study the optimization problem for a different transformer where we do one hidden layer, which I know you've worked on. Yeah. So you might say, oh, maybe I could get a PL inequality. But then even if you achieved that, what would you know about the test performance if you don't have an explicit solution? Yeah, no, it's a good question. So in this other paper I mentioned where people looked at what's happening in the finite finite task setting, they find a way to do this, but it's much more complex. Basically, you have to like analyze the interactions between like 8th order tensors that, it's much more difficult when you don't have an explicit formula like we have here. There is a way to do it, but it's like built upon like 6 years of research on related problems that is pretty complex. Yeah. Okay, so someone is doing it now. Yes, yeah. Okay, thanks. But for still sticking with linear, just doing finite. Yeah, finite tasks. And with stochastic gradient descent. Yeah. I see. Okay, thank you.
Any other questions?
Thank you. So how about from the application point of view? What would you say, what does this mean in practice? Not just this linear version, but like deep and nonlinear. Like, does it mean that in the future it's just all about trying to solve the inverse problem of how to train transformers, and then all the other algorithms are coming out from the transformer itself?
Yeah, I think there's a lot of questions about how this relates to what people are actually doing. And I think the biggest takeaway for me from this is that a big source in the problem of the failure of robustness is the source of the training data, right? So like in our setting, what we saw is that if you have a fixed covariance matrix at test time, then you're kind of screwed when you have a different type of covariate distribution at test time. And that training on more diverse data sets kind of forces the transformer to learn a more robust learning algorithm. I think that's the kind of most easy way of saying something relates to practice. But I mean, the sad truth is, theoretically understanding transformers is really playing like 6 steps behind what's happening in practice. Like there's thousands of people who are just spending all day, every day, coming up with little tricks that make things work better. And the speed with which those things can be done just like completely outpaces what like poor theorists like me and my collaborators can do. Just because these models are so complex, and like even understanding a linear transformer with one layer, like, it was very nice that we had this behavior. The behavior of this equation in green is the exact same behavior as these GPT-2 architectures for supervised learning, this in-context learning setting. But I would be lying if I said that this is really saying something very explicit about what is happening in practice.
Right. So in principle, these like super deep, super nonlinear, superscale models, I mean, there might be some like very surprising properties in them. You cannot say, right? But in principle, can also be that they are pretty similar as the shallow linear one.
Yeah, I mean, I think, okay, like for me, something that was very satisfying from this work was the fact that training on noiseless linear regression buys you good performance on nonlinear and noisy linear regression. Right? This is something that I think is very striking, not something that one would expect, and I think is like a very clear example of a kind of emergent behavior. Like you're training on something simple, but you get something greater than what you trained on. And I think that's something that people are shocked by when they look at these transformers that are trained on like internet data and suddenly seem to be able to do something much more than just predicting the next word.
Yeah, definitely. Yeah. Thank you.
All right. If you don't have any more questions, let's give Spencer one last round of applause. And we have plenty of coffee and tea and snacks at the back, so if anybody wants to stick around and have a chat, please do.